other things the periodic table teaches us isn't just the up-down trends, but the across trends. So let's scroll up a little bit. If I go across a row, so if we look back up here at lithium, then beryllium, then boron, then carbon, then nitrogen. So I'm going across the row. As you go across, you go from larger to smaller. So lithium over here is very big. Beryllium gets smaller. So boron gets smaller. Carbon gets smaller. Nitrogen gets smaller. It starts getting less noticeable, but they continue to get smaller as you go across the periodic table. Now, this is true for each row. As you move from the left to the right, your atomic size will get smaller. This is also true going up. You're smaller at the top periodic table, you are larger at the bottom. So if we think of fluorine to chlorine to bromine to iodine, as we move up the column, we actually get smaller. So the periodic table has a diagonal trend. As you move up and to the right, you get more tiny. So if we were to go and try and compare, let's say we want to compare selenium and argon. Which one would be smaller, selenium or argon? Take a second to think about it. Well, argon is more to the right, and so we're going more to the right, and argon is more up. So argon is going to be substantially smaller than our selenium atom. So just by looking at the position on the periodic table, we can identify rough atomic size comparisons between things. This trend is also maintained for a lot of other behaviors. If we are trying to take an electron off of something, so at the moment these are all written as neutral, but if I want to go lithium plus from lithium, I have to knock an electron off. So somewhere out in space is the electron that lithium lost. Well, if you ever try to pull two magnets apart, right, it takes a little bit of work. They fight you. A negative charged electron is attracted to the positive charged protons, just like opposite sides of a magnet are. So to remove an electron takes energy. And so we have a term called ionization energy. Basically, ionization energy is a measure of how hard to remove an electron. How difficult is it to make it a plus charge? And what we find is that as we go up, it is harder. And as we go to the right, it is harder. So things in the top right of the periodic table, fluorine, helium, these are very difficult to remove electrons from. But things in the bottom left, francium, these are very easy to remove electrons from. In fact, if we go back and look at our alkali metals over here, I said lithium, if you threw it in water, it lightly fizzed. Sodium would catch fire. Potassium would explode, and then rubidium and cesium would explode much larger. What we found is that we went down a column, it got more explosive. It was easier to take that electron off. The reaction happened more readily. And so what we see is that, yeah, it was easier to do to the lower elements because it didn't take as much work to take that electron off, so the reactions that they do happen more readily. And so this kind of trend helps us track reactions and reaction energy and things like that. And so these are some of the trends that we'll find in the periodic table. It's a very useful tool Most of the time what we will end up using it for is following along to find those molecular masses, but we want to be able to look at it and identify some of the other information.